Hi everyone, welcome to week 11 of our biochem weekly reviews. I know that tomorrow is your exam, so I'm hoping that this is a really good review that will prepare for that. If you have any questions, as always, feel free to send them in the chat. So yesterday, your lecture was about gluconeogenesis, which is kind of the opposite of glucose. And one of the most common questions that we get is, but why? Because glucose makes energy, why would we use our energy to just make some more glucose? It doesn't really make a lot of intuitive sense. And so because of that, our very first question is just, why is it necessary? And there's not a super easy answer that I'm going to give, but effectively it's because when we do the math, when we do the math, we see that our body holds about 200, maybe 220 grams of glucose. We require about 160 grams a day. Okay, and most of our glucose, goes to the brain. So if most glucose is going to the brain, but we can't just send pyruvate, we can't send acetyl-CoA, things like that into the brain because of the blood-brain barrier. Okay, these guys cannot enter. So if I exercise, if I'm burning my energy, my glucose, from some way that is running or physical activity, then I have less glucose for the brain. So my body realizes this and it has to compensate. So we have to make more glucose for our organs like the brain, for our organs in which we can't just take in our products from glucose, or from glycolysis, excuse me. So that kind of, the next question is, gluconeogenesis is often described as almost the reverse of glucose. And I always kind of say it's kind of glucose backwards, but not quite. And so it is necessary to say it's almost, or it's not quite, or mostly the reverse of glucose. And here's why. So this is one of my favorite tables to show you guys. I think you've seen, I bring it up a lot. This is the 10 steps of glucose. Yes, there is an 11th in this figure for lactate, but for now we're going to talk about the first 10, the main 10. And in the steps of glycolysis, we see a lot of very, very spontaneous reactions. Right? Reaction 1, incredibly spontaneous. Reaction 3, spontaneous. Reaction 10, spontaneous. If we were to reform glucose, it would require, I believe, I think the number that I remember seeing was about 80 kilojoules per mole of glucose, or per mole of pyruvate going back to glucose. And that's a lot of energy. And so because of that, the body doesn't want to just do this backwards. So what'll happen is when we're going backwards, so this being reaction 1, 2, 3, 4, all the way up to 10 over here, reaction 1 will be different. Reaction 1 being this one. Reaction 1 of gluconeogenesis, excuse me. Reaction 10 will not be the same as reaction 1 of glycolysis. And same with reaction 3, which is going to be reaction 8 of gluconeogenesis. They're going to be different. The rest of these 7 will all be catalyzed by the same enzymes, just in reverse. Okay, because while some are a little bit spontaneous and some are a little bit non-spontaneous, overall, they're okay to work in either direction because they're fairly neutral. They're close to zero in terms of free energy. Okay, so the 3 reactions in glucose that are not present in gluconeogenesis are catalyzed by these 3 enzymes. And I'm sure you guys have noticed this trend, but I'm going to say hexokinase reaction. Even though hexokinase isn't reacting, it's the thing that's catalyzing the reaction of glucose to glucose 6-phosphate. So how does gluconeogenesis reverse these reactions? So just a reminder, like I just mentioned, hexokinase is the glucose to glucose 6-phosphate reaction. And we use ATP and get out ADP. Okay, I just realized I don't have enough room if I draw it that way. Okay, so, and we get out ADP. There we go. Phosphofructokinase is using fructose 6-phosphate, and adding an ATP once again, to catalyze the reaction to ADP and fructose 1,6-bisphosphate. Okay. Finally, pyruvate kinase uses pyruvate with ATP released, and we put in ADP. There we go. Okay. So I'm actually going to take these, and I'm going to tell you guys what's going on with gluconeogenesis for these reactions. And I'm going to do it backwards because I think that it's easiest to think of it in the order that it's happening in gluconeogenesis. So remember, this way is glycolysis. This way is gluconeogenesis. There we go. Okay. So how are we going to convert pyruvate to phosphoenolpyruvate? So this reaction, catalyzed by pyruvate kinase, is very, very ergonic. It's very spontaneous. We can't just do it backwards because that would take a lot more energy, and we don't want to waste too much energy in this process. We use some, but we don't want to waste too much. So the first reaction, excuse me, is going to be the reaction of pyruvate to oxaloacetate. Okay, so pyruvate, I lost my mouse. There it is. Pyruvate using ATP to ADP is going to give us oxaloacetate. Okay, so oxaloacetate, so before I get into oxaloacetate, let's talk about use 1 ATP and we would get 1 ATP out of this. So this reaction is kind of neutral with regard to the forward and the reverse. We would get 1 ATP out of the forward reaction, we use 1 in the reverse, that's okay, right? So oxaloacetate is a citric acid cycle intermediate, or a tricarboxylic acid, Krebs cycle, whatever you call it. It's a part of that, that cycle. And so this takes place in the mitochondria. Okay? Mitochondria. And we're going to talk about the significance of that in the next question. I just want to make sure that I bring that up. Okay? Oxaloacetate obviously isn't PEP. Okay? The next step, catalyzed, I forgot to include the enzyme. The first one, this is catalyzed by pyruvate carboxylase. Pyruvate carboxylase. Okay, second reaction, catalyzed by PEP carboxykinase. So not carboxylase like the other one, carboxykinase. Okay, so kinase, well, the rest of these are all kinases. What do those have to do with each other? We're going to use not an ATP this time, but a GTP. Okay, GTP to GDP. So while we always consider ATP our main unit of energy, it's important to recognize GTP is about equivalent to ATP, especially because it's they're both excuse me, nucleotide bases with 3 phosphate groups. The cleavage of that third phosphate group is very, very exergonic for both, so we treat them as about equivalent. So whereas the first reaction from pyruvate to oxaloacetate, we said we're kind of energy neutral between the forward and the reverse. Here we're seeing we're no longer energy neutral. It takes 2 equivalents of ATP, and we would only get 1 out of the reverse reaction. So gluconeogenesis is costing us energy. Okay, that's the first important thing to keep in mind. Okay, so now shifting gears to the next reaction. Excuse me. So fructose 1,6-bisphosphate, fructose 6-phosphate. Okay, so this one is a little bit easier because, well, it's just one reaction, no more 2 reactions to do one thing. And this one reaction is catalyzed by fructose 1,6-bisphosphatase. Fructose 1,6-bisphosphatase. Okay, and in this reaction, we release one inorganic phosphate. Okay? Phosphate. So let's think about what that means. Okay? So oftentimes, I'm going to be writing over on this right side. Oftentimes we see the idea that ATP, when you form ATP, when you make ATP, you get ADP plus inorganic phosphate. This inorganic phosphate is just a phosphate group, really. I don't know exactly why it's called inorganic, to tell you guys the truth. It's just what it's always been called. And so the thing is, that's not giving us energy, right? The reason that ATP is very high energy is because of the phosphates attached to each other. So this is kind of energetically meh. So when we look over here, fructose 1,6-bisphosphate is kicking off one of its one of its phosphates. It's kicking off the one that's attached to the first position. But we're not getting ATP out of it. We're not getting any high energy things out of it. Okay? So now we were down one ATP from the pyruvate to PEP reactions. Now we're down another ATP from the phosphofructokinase reaction. Okay? So finally, let's deal with glucose 6-phosphate. And this one is almost exactly the same as fructose 1,6-bisphosphate because it's catalyzed by glucose 6, phosphatase. And once again, releases an inorganic phosphate. Okay, so we've lost the equivalent of 4 ATP from this reaction. Okay, it's not a great reaction energetically, but we're not doing this just because we want the energy now. We're doing this because we need the glucose somewhere else. We need the glucose in the brain. Okay, so looking back at, before we jump into the next section, when we look back at, let's see, was it week 10? It was not week 10, it was week 9, excuse me. So looking back at week 9, one of the things that I talked about quite a lot was this idea here of the catabolic mode goes through enzyme 3, the anabolic goes through enzyme 6. And that's because enzyme 3 is really, really spontaneous. So we go through a different pathway and we go backwards. So we talked a lot as well about these are the points we're going to regulate. E3 and E6 are the points we're going to regulate. So as we move into the next few questions, I want you to think about which enzymes are we regulating? Which enzymes do we regulate in the forward direction? Which could we regulate in the reverse direction? Okay. So this is gluconeogenesis, right? You start with, let's see, where are we? Pyruvate. Pyruvate enters the mitochondria, converted to oxaloacetate. Oxaloacetate leaves the mitochondria and is converted to phosphoenolpyruvate. We have these same reactions up till this point, when now, rather than using phosphofructokinase, that's not happening, you're going to use fructose bisphosphatase, or fructose 1,6-bisphosphate. This reaction is basically the same. Finally, fructose 6-phosphate is removed by fructose 6-phosphatase and formed into glucose. And this is in the liver or the brain. Okay? So, the question is, this is gluconeogenesis. Why is location so important? Okay? So, this is kind of 4 questions in one, to be honest. So, first reason that location is important is because this compartmentalization, pyruvate in the mitochondria specifically, is essential because of what we just talked about before I started this question, regulation. Pyruvate going backwards has to be highly regulated. How is it regulated? Acetyl-CoA and citrate. Okay, so let's talk about these. So pyruvate carboxylase, because it's the reaction that converts pyruvate to oxaloacetate, has to be in the mitochondria. It is it's this PC that we see right here. This is pyruvate carboxylase. It's in mitochondria. So if there's a high concentration of acetyl-CoA, that means that we've got energy. right? Because acetyl-CoA can go into the TCA cycle and make a ton of ATP. So a high level of acetyl-CoA tells us we've got a lot of energy, and it'll activate pyruvate carboxylase to start oxaloacetate, start conversion to oxaloacetate, and then pyruvate. Sorry, I'm not sure why it just echoed there, but I guess moving right on since it stopped. Compartmentalization, location, is important for, first of all, regulation. I want to mention ATP is also an activator of pyruvate carboxylase in the same way that acetyl-CoA is. They indicate high energy status. High energy status means we don't really need more energy. Let's send pyruvate back. Okay? The next thing that we have to ask ourselves is this whole thing with liver, brain, and blood. So we talked about when we first learned glycolysis that this glucose 6-phosphate, now that it has a negative charge, it's stuck inside the cell that we're dealing with. So when we remove that negative charge in the liver, in the brain, wherever it is, it can now travel back into the blood. Okay? The location is very important because the location determines where in the body the location meaning the compartment that it's in, determines where in the body that your glucose can be, and it helps us regulate this very carefully. Because pyruvate outside the mitochondria, we don't know if you have a high amount, we don't know if you have a low amount, right? Pyruvate is that most connected metabolite. If pyruvate's entering the mitochondria, then it's most likely going to undergo pyruvate dehydrogenation into acetyl-CoA and then the TCA cycle. We can stop that if there's already a ton of acetyl-CoA. So that's what compartmentalization is so valuable for here. Okay. So next, how do we get oxaloacetate out? Okay. And it's really, really kind of unintuitive in my head because it doesn't make sense that for oxaloacetate, oh, actually, before we get into this, I realized I forgot something with number 4. Pyruvate carboxylase being in the mitochondria is also really valuable for another reason. The pyruvate in the cytosol, in the cytoplasm, is pyruvate that was just formed. If pyruvate that was just formed is right next to pyruvate carboxylase, what we're doing is we're saying we're allowing gluconeogenesis to occur right then while we're already having glycolysis. Okay? So by allowing for pyruvate carboxylase to be in the mitochondria, we can prevent the simultaneous glycolysis and gluconeogenesis that would just waste energy. Okay? That's one other really important reason for this compartmentalization, for this location factor. So now moving into number 5, I apologize for the confusion. How is oxaloacetate moved from the mitochondria to the cytosol? So you don't just take oxaloacetate and let it leave the mitochondria. I'm not sure, I believe it's something to do with the charge if I remember correctly. Oxaloacetate can't leave. It can, however, be converted to malate, and then malate can leave. So let's pause. Oxaloacetate, I've been telling you guys, is a TCA intermediate. So is malate. Okay? This is one of the really resourceful ways that our body has to recycle our resources. We don't need separate enzymes to kick malate out. We don't need separate enzymes to get pyruvate out. We have pyruvate carboxylase, and then when you have oxaloacetate, you guys haven't really learned the TCA cycle yet. But basically, you have acetyl-CoA here. Acetyl-CoA enters the TCA cycle and helps oxaloacetate be converted to citrate. And then all the way around, you've got several reactions. Over here is the malate dehydrogenase reaction to oxaloacetate. This reaction is, like most reactions we're talking about, reversible. So all we're doing is using what's already here. We're using this infrastructure to just do it backwards and kick malate out. So when you've got a really high oxaloacetate concentration, because you've converted pyruvate to here, and a really high acetyl-CoA concentration, you could do a ton of the TCA cycle, or you could, as equilibrium would tell you, form more malate, malate can be kicked out, like we see here. Malate can be kicked out of the mitochondria, reform oxaloacetate, and then be allowed to not be allowed, excuse me, be able to undergo gluconeogenesis and be converted by pyruvate carboxykinase. Yes, pyruvate carboxykinase. Apologies, I know that, or no, I'm sorry, PEP carboxykinase. I always get those two mixed up. I apologize. So that's the basic idea behind this compartmentalization, behind oxaloacetate. The next question is, how can oxaloacetate be converted into phosphoenolpyruvate, into PEP? Okay. So last week when we were talking about glycolysis, I really emphasized phosphoenolpyruvate to pyruvate is favorable because PEP is relatively unstable as an enol, right? By getting rid of its phosphate group, it can take the keto form, and that's what drives that reaction forward to convert it to pyruvate. And here I'm telling you, we're going to convert oxaloacetate into phosphoenolpyruvate. We're going to get over that whole energy problem because we want to. Okay? So the important thing to keep in mind is, first and foremost, we're using energy here. If we look right here, or I'm sorry, right here in this drawing, which I'm not sure how well you guys can see, but I'll highlight it. The PEP carboxykinase reaction uses GTP to GTP. So right off the bat, we need to recognize we're using energy. Okay? So let's look at this. So this is PEP. Like we said, it is, I apologize, I've lost my mouse. There it is. Okay, sorry, I was trying to highlight. We have this enol, not very stable. And we've got a phosphate attached to it, so it's really not happy. Okay, so oxaloacetate being converted to it is driven by GTP hydrolysis. Okay, the hydrolysis of GTP, the delta G naught of ATP/GTP hydrolysis, because they're relatively equivalent, hydrolysis is, like we said, about -30.5 kilojoules per mole. The delta G of this reaction, which I'll draw, I can find my mouse, there it is. Delta G of reaction here is about -22.5, -2.6 kilojoules per mole. In other words, if we were just trying to convert oxaloacetate to PEP without GTP, that would be a delta G of +8 kilojoules per mole. It would be very, very spontaneous, or I'm sorry, non-spontaneous. That's why GTP is here. That's why we have to use this energy, because we need it. Okay? Otherwise, it would just be way too non-spontaneous to work. Right? So when I told you guys about the metabolic pathways, I really emphasized, think about how we can regulate this. And also fructokinase is one of, if not the most regulated enzymes we basically ever deal with. So the same is true of its reverse, of fructose 1,6-bisphosphatase. And your professors have what I think is a really, really great slide that I'm just going to, it's down below, ignore that. I skipped ahead a little. So fructose 1,6-bisphosphatase. So we talked about PFK inhibited by citrate and ATP. So these two tell us we have high energy status, so we can stop working on PFK. We're good. Well, these two also activate, and I'm going to abbreviate it, fructose bisphosphatase. Just for convenience, they activate this. Does that make sense? Yeah, right? It's called and I kind of spoiled it in number 8. It's called reciprocal regulation. Okay, so the steps that are different, that have different enzymes effectively, PFK versus FBP, these steps are reciprocally regulated. When one is inhibited, one is activated. When one is activated, the other is inhibited. And so the other ones that I mentioned are inhibited by AMP. I'm sorry, that I haven't mentioned is PFK. PFK is activated by AMP, which means that FBP is going to be inhibited. Activated by AMP, inhibited by AMP. And that makes sense as well, because AMP tells us we have very low energy. Low energy tells us we need glycolysis running. Making glycolysis running means let's stop on gluconeogenesis because we don't want to waste that energy. Okay. Like I mentioned, this is called reciprocal regulation. Reciprocal regulation. It's important because this is the reason that our metabolic pathways can be so similar. It's the reason that we can use the same enzymes for reaction 2 and then 4 through 9 of glycolysis as we do in the reverse reactions for gluconeogenesis, because the other ones are inhibited and activated in opposite, or like with each other, in order to allow the reactions to occur only when we want them to occur. Okay. What is the role of PFK2 in glycolysis and gluconeogenesis? This question is one that I kind of gloss over with glycolysis because I knew this chart was coming, and this is the one that I really, really like. And this really shows what I would have wanted to say. I couldn't show without knowing gluconeogenesis. So here it is. I'm going to zoom out just a little bit. Okay, you can see the whole thing. So the left side, glycolysis, the right side, gluconeogenesis, right? So we start off with fructose 6-phosphate. So we're starting here. And it can be converted to fructose 1,6-bisphosphate by PFK. So let's follow that arrow back, and we get all the way down here. Fructose 2,6-bisphosphate. Fructose 2,6-bisphosphate activates glycolysis and inhibits gluconeogenesis. Okay, so how is that regulated? When fructose 6-phosphate, or fructose 6-phosphate can be phosphorylated, excuse me, by PFK2 into fructose 2,6-bisphosphate. Okay, so PFK2 and PFK2 phosphorylated are really affecting here. PFK2 is activated by higher concentrations of fructose 6-phosphate. So let's think about that. Fructose 6-phosphate means we have going backwards, kind of, when we keep trending backwards, we have glucose. When we have a lot of glucose, when we have high blood sugar, we get a good amount of fructose 6-phosphate. Fructose 6-phosphate activates PFK2, which phosphorylates fructose 6-phosphate into fructose 2,6-bisphosphate, which then activates PFK1 to make fructose 1,6-bisphate to go through glycolysis. On the other hand, when we have low blood sugar, glucagon is released, and glucagon wants to raise our blood sugar. How does it do that? It phosphorylates PFK2 to inhibit it, and in doing so, it favors the, I should say, PFK2 actually changes as an enzyme. I don't know that that's something that's always super clear. I think it's a really confusing part. A phosphorylation of PFK2 converts it into fructose 2,6-bisphosphatase. Okay, so this is a bisphosphatase. And exactly like the arrow next to it shows, that favors more fructose 6-phosphate. Okay, that also, because we're not activating PFK1, that means that we're inhibiting PFK1 and thus activating gluconeogenesis. Okay, so this is no longer happening, which means this can happen, which means we get more fructose 6-phosphate, and once again, like we did over here, go all the way back, and we see that means that we get more glucose. So phosphofructokinase 2 is kind of the key to that regulation to keep our blood sugar where it needs to be, with insulin, with glucagon, and really with phosphofructokinase, okay? And once again, I'm going to ask, Does this make sense? It comes down to the idea that that PFK1, phosphofructokinase 1, the committing step of glycolysis. Once we hit PFK1, we're good to go. We're doing glycolysis. So we want to make sure that we're only doing it when we need it, and that when we're not, we raise our blood sugar so that, or I should say, when we're doing it too much and we have a low blood sugar as a result, we can raise our blood sugar and keep ourselves where we need to be in terms of equilibrium. Okay? And that's what makes phosphofructokinase 2 so important to glycolysis and gluconeogenesis. Okay. So this is the complete metabolic pathway that shows everything. So let's kind of take this away. So we know the left side. Again, the left side is glycolysis. We talked about this last week. We're happy. Pyruvate or lactate. So like we now going back up, because I do want to briefly mention this, in the mitochondrial matrix, we convert to oxaloacetate, and we back into the cytoplasm, go to PEP, go all the way backwards, yada yada. Okay, fructose 1,6 bisphosphate to fructose 6-phosphate, and then the last reaction of gluconeogenesis occurs in the endoplasmic reticulum. That's weird. I'll say it. We haven't talked about the endoplasmic reticulum all semester, really. We've been dealing with the mitochondria, we've been dealing with the cytoplasm, and now out of nowhere, we have a reaction going on in the endoplasmic reticulum. Again, that's weird to me. So that's why I wanted to talk about this. So the enzyme is associated with the endoplasmic reticulum. Why? Once again, compartmentalization. So this diagram here shows us that exact thing. When you have glucose 6-phosphate in the cytosol, remember, glucose, so the next reaction glucose 6-phosphate would undergo in the cytosol is the fructose 6-phosphate. It's the phosphoglucoisomerase reaction. That reaction is fairly neutral. So if you have glucose 6-phosphate in the cytosol, we're not sure that we're going to go back to glucose. So by having this transporter here, which by the way circumvents the whole negative charge means in the cytosol, having a transporter, having this ER-associated protein means once again we can compartmentalize. So this breaks down glucose again, and it gets us back into the plasma membrane with regular glucose. Okay, so I want to point this out for a couple of reasons. First, compartmentalization. It is so vital for glycolysis, for gluconeogenesis, for most of our reactions for this exact reason. We only want to do this reaction for gluconeogenesis when we have a ton of glucose 6-phosphate. When we don't, we stay in the cytosol, we let ourselves go through regular glycolysis. Okay? Now the other thing I want to mention is this is one difference between the brain and the rest of the body. So the whole major reason that we end up doing gluconeogenesis is if the muscle or the brain need glucose and they're stuck somewhere else, and the energy is stuck somewhere else. So this enzyme, the glucose 6-phosphatase, is not present in the muscle or in the brain. They don't make glucose because they're only ever going to use it. Okay? That's a really important topic. Okay. So, number 11. What is the total use of energy in gluconeogenesis? The gluconeogenesis we talked about a little bit, so let's go through this. We use 1 ATP and 1 GTP. That's over here. 1 ATP, 1 GTP. It's important to recognize this is per 1 pyruvate. Pyruvate is a 3-carbon structure, and as we go all the way back, we end up needing 2 pyruvate to reform our fructose 1,6 bisphosphate. We need to double this. So we really use 2 ATP, TP, and 2 GTP for gluconeogenesis. The third thing is, excuse me, that We also end up using 1 ATP here in the 3-phosphoglycerate to 1,3-bisphosphoglycerate reaction. We use 1 more ATP, and that's per pyruvate, so we double it. So times 2. So we end up using the equivalent of 6 STP, so ATP, GTP, whatever it is. Okay. The use of these 6 makes gluconeogenesis overall exergonic. So the total delta G naught prime of gluconeogenesis, which I'm just going to abbreviate GNG, is about negative 38 kilojoules per mole. Now that number is significant because remember that these are each about negative 31, right? So this is the reason, negative 31 or negative 30.5. I use them kind of interchangeably, if you guys didn't notice from earlier. This is the reason that gluconeogenesis can work even though we're getting ATP out of glycolysis. And like we said earlier, the reverse of glycolysis would just consume 2 ATP and it would be endergonic. It wouldn't want to work. Okay. Whew. Okay, so that is, oh wait, okay. All right, so just a quick recap of the cycles, regulation of glycolysis and regulation of gluconeogenesis, really. So I really want to focus especially on this reaction with fructose 6-phosphate and fructose 1,6-bisphosphate and the PEP pyruvate reactions. So fructose 2,6-bisphosphate activates the forward reaction and inhibits the reverse reaction. Same with AMP, same with AMP. ATP and citrate inhibit this forward reaction and they activate the reverse reaction. I'm not sure why it's not showing on this side, but they do according to some of your slides. Okay. Now there's a lot here in the reaction 10, the peptipyruvate reaction. Fructose 1,6-bisphosphate activates this reaction. Let's think about once again why that is. Fructose 1,6-bisphosphate is right here. When you've got high concentrations of this, it means that you want this reaction to occur so that you can decrease the PEP concentration and decrease this through Le Chatelier's principle. Okay. Acetyl-CoA inhibits the forward reaction because when you've got, and same with ATP by the way, because when you've got high concentrations of those, you have high energy status. High energy status means we don't need more. Okay, that's also why acetyl-CoA activates the reverse reaction. Okay, alanine and camp-dependent phosphorylation are somewhat minor. I don't see them asked about often, if at all, but I do want to make sure that I at least bring them up because they are somewhat important. Okay, so once again, this comes down to that idea of reciprocal control, reciprocal regulation. Right, one is inhibited while the other is active. Because without this, it would be futile, right? We would make 2 ATP and then burn 6, make 2, burn 6, make 2, burn 6, all at the same time. All we would really be doing is wasting 4 ATP per complete cycle from glucose back to glucose. We would just completely waste our time. Right? That's why it's governed by the status. High energy, pyruvate is going to be used to make glucose, to make glycogen, or to make glucose for the brain. At low energy, glucose is degraded, we get more ATP, we're happy. Okay? That's what it really comes down to. So I'm going to pause for a moment. If anyone has any questions now, please feel free to ask. I know that gluconeogenesis is not super intuitive. All right. So the rest of this chapter, your professors do something that I personally think is fascinating, and they talk about ketone bodies and keto diet a little bit. However, that said, I've never seen that asked on an exam, and so I don't want to waste anyone's time since I know everyone's kind of stressed for tomorrow. So I'm going to go ahead and skip over that and kind of broaden up the last thing I said and say, does anyone have any questions about any of the content for this exam? Not just gluconeogenesis, not just glycolysis, the entire exam. Okay. All right. So I prepared a couple of questions just so that we could talk about a couple of what I think are the most important topics of this exam, with a brief asterisk that there simply isn't enough time to talk about all of glycolysis, and that's all very important. So while I won't be talking about glycolysis in a ton of depth, watch last week's recording, study that separately. Whatever you need to do, make sure that you know glycolysis well, even though I can't really talk about it much. Okay? So the first question that I think is really important to review is those models of enzyme regulation, the MWC and the KNF. Okay? So just very briefly, the difference between them is the MWC is called the concerted model. It all happens at once. The KNF is called the sequential model, or the ordered model. I use sequential because I think it's a little bit easier to see. So a brief overview of each of them. The MWC has a relaxed form, R0, and a tense form, T0, and they're in equilibrium with each other. This is the one substrates bind to. The tense form can't bind to substrate. So activators bind to the relaxed form. Plus an activator, which we'll label A, and form what's called R1 with an A. So R1 now has more activator binds per Le Chatelier's principle. Since this is going down, the tense form compensates. Okay. On the other hand, if you have an inhibitor, that inhibitor binds to the tense form inhibitor, and you get T1I inhibitor. Okay. And this does the same thing as the activator, but on the tense form side. This shifts to decrease the amount of T0. As a result, equilibrium, Le Chatelier's principle, we compensate. We decrease the amount of R0, which decreases binding. Okay, that's how activators and inhibitors work. When you bind substrate to R0, you can get a very similar effect as an inhibitor. That's kind of how cooperativity can be explained by MWC. KNF does a really great job at explaining cooperativity, both positive and negative. So I'd like to talk a little bit more about that. So the KNF model is, like we said, it's sequential. So you have this square and this square. So this is subunit 1, which I'll just name 1, and this is subunit 2, which I'll name 2. So when 2 binds to a substrate, it gets changed. So now, now it looks like this. And I'm going to put a 2 up here, and it's shaded in because now it's bound to something. Okay, so the shading means that there's a substrate in here. Okay, 1 is still as it was. However, here we go. 1 can, I should say, the substrate binding to subunit 2 induces a conformational change in subunit 1. That conformational change could be as simple as, because the substrate bound to subunit 2, they have to the 2 subunits bind a little bit differently and they rotate. It could be that simple. When it does that, one becomes 1 prime. Okay. So now, if the original form, or I should say, if the new form binds to substrates better, so if this is more easily able to bind to a substrate than this, we get positive cooperativity. Positive cooperativity. If, on the other hand, we covered up our binding site or something like that, we get negative cooperativity. Okay. Cooperativity. And hemoglobin is a great example of both of these models. It's also one that you guys need to know for your exam because they love testing about hemoglobin and myoglobin. And especially hemoglobin, they want to know a ton of details. Okay. So we're going to review very briefly in the second question, how does hemoglobin show aspects of both models? So very briefly, and I'm going to have to use a few different colors for this, hemoglobin hemoglobin has two subunits. Or, I'm sorry, it has four subunits. Two are alpha subunits, which I'm coloring in blue. And two are beta subunits, which I'm putting in green. Okay. So alpha and beta. The first step is a substrate binds to the first alpha subunit. Okay. So this thing is bound, and there's a conformational change in it. There we go. Okay. And then two beta subunits are normal. Okay. This conformational change in the first alpha subunit causes, so hemoglobin, very briefly, just to recap kind of, because I forgot to tell you guys its structure. It's got four rings surrounding an iron in the center. This iron is normally slightly out of the plane of the rings. So the rings are all flat right here. Iron just rests slightly above them. There's not a ton of space for it. But as soon as that first subunit binds, it changes its shape just a little bit to allow iron into the plane of the ring. Iron into plane of all the rings, so of the hemoglobin, really. And when that happens, that induces a conformational change in the second alpha subunit. Sorry, don't know what just happened there. So, subunit 1 bound, subunit 2 conformational change. That conformational change, okay, that should be, that conformational change allows it to bind more easily to a substrate. Now we've got two of the subunits of hemoglobin bound to two oxygens. Okay. At this point, all we've been doing is KNF model. So this whole thing has been KNF, right? And it's perfect that we kind of finished in this amount of time space, because now I need to go working again. So now this is going to typically be our tense state in equilibrium with a relaxed state. And the reason that we have a tense state and a relaxed state is because at this point, once two oxygens have bound, once your alpha subunits have both bound, there's another conformational change. Your subunits rotate about 15 degrees relative to one another. And what that does is it opens the beta binding sites more effectively. Okay? So now your beta subunits, or I should say your alpha subunits, still have their oxygen. Nothing's changing with them, except, you know, my poor drawings make them look slightly different. Now your beta subunits are in a different form. Okay? Your beta subunits being in a different form means they're more easily able to bind, and you get plus two substrates. Okay? So the reason that we have this sequential, I should say this is the MWC model. I know I said it earlier, but I want to make sure that I emphasize it. So the reason that we get this is the first step is classic KNF, right? We have one subunit binds, induces a conformational change in the second subunit binds. Right? Positive cooperativity, KNF model. That shows us, excuse me, that shows the sign of the KNF model because it's one subunit inducing conformational change in the other. That's sequential, one after another after another. The MWC model, rather than a single beta subunit changing, we see both beta subunits change. We see this entire molecule change into a form where it's more easily able to bind with all of its remaining subunits. That's concerted. Everything is happening at once. So that change is all making a difference at once. And that's why R0, that's why we can call the T0 and R0 forms what we do. Okay? So that's hemoglobin. I want to very briefly mention myoglobin because it is important, even though we don't really talk about it much, because it's a little bit easier to understand. Myoglobin does not show cooperativity because it's a monomer, because it doesn't have multiple oxygen binding sites, things like that. Whereas hemoglobin does show cooperativity, and that's why its Michaelis-Menten curve is going to be sigmoidal. Right? It's not going to look like this. oh, that's a terrible drawing. It's not going to look like this. This would be myoglobin. This would be hemoglobin. That's that. Number 3, where are metabolic pathways regulated and why? So I think I've kind of hit this topic so much that you're all tired of it. So I'll just very briefly say it and we can move on to the next one. So metabolic pathways are regulated at the sites where catabolism and metabolism use different enzymes. And why? So that we can reuse all the same enzymes and it's more efficient. Okay, I'm just going to move on. So is the following image an aldose or a ketose, and how can you tell? So this is from the carbohydrate chapter, one that we don't talk about a ton, but is still very valuable. So aldoses, their carbonyl is an aldehyde. Ketoses, their carbonyl is a ketone. You see that this is the carbonyl. It's attached to 2 carbons, which makes it a ketone. A ketone makes this a ketose. Okay, fairly easy. Just wanted to make sure that I mentioned it because it is a question that is somewhat frequently asked. Okay. So is it an L isomer or a D isomer? So when we do that, we number, so just a quick recap on numbering. We number aldoses from the carbonyl. So their carbonyl is going to be in the first position. Actually, it's normally drawn CHO, so let me change that real quick. CHO and then CHOH, etc., all the way down. This is carbon number 1, this is carbon number 2, 3, and so on. Ketoses are similar, except we don't have a single, we don't have a carbonyl on the end, so we can't name it 1. We pick the side closest to the carbonyl. So this is 1, 2, 3, and so on. We look at the last chiral carbon to see if it's an L or D isomer. In this case, since 6 is not chiral, look at carbon number 5. If the OH is on the right, it's a D isomer. OH on right equals D. OH on left equals L. And I like to think it that way because the L, so it makes sense. So draw the other isomer. So if I were to draw, apologize, it's taking me a moment. And while I am drawing this, I want to mention very briefly, this is fructose. I don't know if it's one of the ones to memorize, but I thought I'd use it because it oftentimes is. So I thought that it would be one of the easier ones that I could use and most applicable. If I were to draw this, so this has an OH on the left, then on the right, we need to swap this one around, so I can draw carbon number 3 on the left with the OH, carbon number 4 on the right, they were before, and just swap this one, can't I? So the answer to that is a no. And this is a mistake that I see very, very often, and one that I made way too many times. The other isomer is not just an isomer at the 5th position. The other isomer is an enantiomer. Right? With enantiomers, every chiral carbon has its chirality flipped. Okay. Now we don't have to assign chirality for this class, thankfully. So all we need to do is switch the order of every chiral center. So carbon number 3 is on the left with the D fructose. It's going to be on the right with L fructose. Okay. Carbon number 4 has OH on the right. We're going to draw OH on the left. Number 5 is obviously on the left, as that's the one that makes it an L isomer, and finally CH2OH. So this is not L fructose. This is something else entirely. This is L fructose. And this is D fructose over on the left. Where I'm drawing. There you go. D fructose. Okay. It's very, very important to make sure that we know that it's an enantiomer. Okay. All right. So what is the difference between amylose and amylopectin? I've asked this question before, but I wanted to bring it up again to remind you guys polysaccharides exist. You might have to memorize several of them. I don't know. That's a professor-dependent question. So, very briefly, the answer to this one, for the sake of your time, I want to go a little quicker. This one is going to be D. Amylose is linear. Amylopectin is branched like that. I want to point out they're all alpha linkages. They're all alpha glycosidic bonds. No beta bonds in either of these. No beta bonds. Okay. Okay. I'm going to pause for a moment because I know polysaccharides are one of the confusing ones we don't really like. So if anyone has any questions, please feel free to ask. And the very last question is, why would the body undergo lactic acid fermentation when the TCA cycle and electron transport chain give so much more energy? Okay, so I'm going to give you guys a second to think about this because it is a little bit tricky. Basically, these are the equations. They're not balanced, but this is a really good indication. So we start with glucose. We get our 3 carbon chains. I'm not going to worry about them. They're not super important to this. We get H plus and H2O. We really don't care too much about those. They're all the same. And then finally, this part is the same across both reactions, so we're not going to worry about it too much. So really, the only difference between pyruvate and lactate reactions is the presence of NAD plus and NADH. So we talk a ton about how NADH is reducing power. We want this reducing power so that we can do future reactions. It's great. But we don't just need NADH. We need NAD plus. Right? When we have glycolysis going on, we need NAD plus so that we can convert it to NADH, and in the process, convert other substrates into the next steps for glycolysis. So lactate, while not super great for us energetically, we're wasting this NADH effectively. We're regenerating NAD plus by lactate for further glycolysis. So remember that we do lactic acid fermentation for 2 reasons. First, anaerobic environments. If you have an anaerobic condition, you cannot easily oxidize NADH back into NAD+. So lactate is there to do that because we have it there, because we can't go through the TCA, the electron transport chain, etc. Okay. On the other hand, for the other reason is this is fast. The electron transport chain is very slow. If I'm working out, if I need the energy right now because I'm running a race or something, I need the energy. TCA isn't going to help us very much. Electron transport chain isn't going to help us very much because they're slow. So lactic acid fermentation happens very quickly, and I can just very rapidly just react into the next. Regenerate my NAD+, do further glucose a lot quicker. Excuse me. Okay. So that said, does anybody have any more questions for us, or for me, before your exam tomorrow? I tried my best to kind of review a couple of the salient points, but of course, review glycolysis in depth. If you need any help, please come into our drop-in tutoring center. Yeah, that's all I have for you guys. Thank you so much. I'm going to go ahead and stop our recording.